In this particular video, I go over the basics of lines and planes. Now, we need, for the future, a simple way to represent geometric objects. We're going to be looking at a collection of things, which we call vectors, and they are going to live in some kind of environment. The easiest analog for us in the plane and in 3-space is lines and planes. There are, though, 4 different but related ways to represent lines and planes, and they change only slightly in R2 and R3. Some of these forms I'm giving to you so that you know about them. We honestly don't use them very often at all, but others are there and we use them all the time. So let's go and try to find a vector way to go describe a line. So let's suppose we have a fixed point x naught, y naught. We'll just call that point P, and a point Q, which would be x comma y, be any point on a line. So I want to find out a equation that represents the relationship between x and y, the xy coordinate of the unknown point Q. But I want to do it using vectors. Okay, so to do that, I need a way to represent slope then with vectors. But see, all a vector is a way to describe the overall net change, the displacement, to carry one point to another. So we'll use a vector d to represent the slope of that line. Now, if it's a vector of 2 components, the first component is the change of x. The second component is the change in y. So the ratio of those 2 components, change in y over change of x, second component to first component of the direction vector, that's actually the slope of this line. So I've now put that vector that represents the direction vector on the line itself. You can see it's parallel or it's lying on the line. Next, we're going to use 2 vectors to describe the position of point P and point Q because these points correspond to vectors in a categorical simple way. All these vectors are in standard position going from the origin to the point. Notice that if I was able to figure out what the vector x is in terms of the change from the origin, I could tell you where the point Q is and therefore give you the relationship between the x coordinate and the y coordinate. Well, now to do that, notice that there is a difference of vectors between x and p, and that goes from the terminal ends of vector x and p, since x and p are in standard position. And we go x minus p, the arrow goes towards point Q and away from point P. Next, also notice though that x minus p and d are parallel to each other. Since they're parallel to each other, that means an x minus p must be some multiple of d. I just don't know what that multiple is. I'll call it t. By just solving for the vector x in that equation, you get the vector x is equal to the vector p plus t times the vector d. And that is what we call the vector form of the line. You give me any single point on that line, there's always some scalar. So the vector x, which points from the origin to this point on the plane, is going to equal to the vector p plus t times d. Let's go ahead and try it once. I would like to know what is the vector form of the line passing through the point 1, 3, and whose direction vector is d? Well, which is -3, 4. So that's easily done because since I have the point P, the vector P is then just the vector 1, 3. That goes from the origin to the point P. So by just what we've done, the vector x is equal to the vector P, 1, 3, plus t times the vector D, -3, 4. If you like, you can replace the vector x with its components, and let's, instead of writing the vector as row vectors, we'll write them as column vectors. That would then be the vector x is x, y. That goes from the origin to the point on the line. That would then equal the vector 1, 3, and to that you add t times the vector -3, 4. And that's it. That's the vector form of the line. It's not really difficult at all. Now that we have the vector form of the line, the next form is called parametric form. They really are directly equivalent to each other. The only difference is that vector form emphasizes the use of vectors, and parametric form emphasizes the components. So let's suppose that we write that the position vector for the point on the line, which we'll call vector x, is the vector in column form xy. The vector p is the vector that points to the point that we know about on the line, the fixed point. That's x naught, y naught in column form. And d is going to be the direction vector that represents the slope. So we have m1 and m2. m1 being change of x, m2 being change in y. The slope of the line, like you're used to, would then be m2 divided by m1. Notice that if you have vector form, all we have to do is just replace the vector notation with their components. And then from here, just multiply out the right-hand side because you're just adding vectors. You know how to do that. And then two vectors are equal if and only if their components are equal. That gives rise then to these two equations. That's called parametric form. Again, the only difference between vector form and parametric form emphasizes the use of vectors, while parametric form is trying to focus on the individual components. Let's just go try one real quick. None of this is very difficult. Given the vector form of the line below, what is the parametric form? You literally just multiply things out to get that x is equal to 1 plus 2 times t, and that y is equal to 3 plus 5 times t. All I did was just add this vector up to be one vector with components. And then since both vectors on the left and the right are equal, that means the corresponding components are equal. You can then just undo this process. So if you want to find the parametric form of the line here, and then what's the direction vector, you could write that this line in parametric form can be written in vector form as x, y is equal to -1, 2 plus t times 3, 9. That is one way to do it. But now, in both cases, though, you notice that you use pretty much directly the direction vector in the formula. Students often get confused and think there is the direction vector. There's only one. No. Any vector that's a multiple of the direction vector describes the same slope because you're still describing the same relative changes. So here, if you like, for example, I could take this particular vector, I could divide it by 3. That would then be the vector 1, 3. And then I could write down the line x, y is equal to -1, 2 plus, let's say, s times this vector. And that's actually the same line. It describes the exact same line. It just uses a different direction vector. The only thing that separates the lines then is the association with parameter values and points on the line. Notice for this first line that if I were to use t equals 1, that corresponds to the point of, we'll just plug in 1 there for t, and you would get 2, 11. But in the second line, with a different direction vector, still the same line, it does have a different association, though, with choices of the parameter and points. Here, if s is 1 in the second line, that would then correspond to the point, which would then be 0, 5. Both of these points are on both lines because it's the same line. This is just different representations for those lines. And having that kind of flexibility is certainly useful. So the vector form and the parametric form are the forms that are most useful for us, for lines at least. But there are other forms. There's also what's called the normal form. Normal form gives rise to the form that you're used to in algebra called the general form. So let's just go back to what we had before. We have some fixed point P, x naught, y naught on the line. We have some unknown variable point on the line also, x, y, we call that Q. We have two vectors that are going from the origin out to these points, which we call the vector x and the vector p. Vector p doesn't change. Vector x can as Q moves around. you get a difference of two vectors, x minus p. That vector is actually on the line, and it represents the displacement from point P to get to point Q. So this time what I want you to do is don't pick a vector that represents the slope. Instead, we're going to pick a vector that's normal to the line. That means orthogonal to it. Now, any vector works. Give me any vector that you know is orthogonal to that line, to every vector that lies in that line. Now, if that vector n is, in fact, orthogonal to the line, then n and the vector x minus p, their dot product, has got to be 0. That gives rise then to the normal form. All you have to do is distribute the dot product through, and then just write the dot product of n dotted with p on the right-hand side. So the normal form of the line is written as n dotted with x is equal to n dotted with p. It is not really useful because you have to write the dot products out as between two vectors. It's not that great. But we can do it. So what is the normal form of the line passing through the point -1, 2 with a given normal vector of 2, 3? It's quite literally just writing down the formula. So we have the vector n dotted with the vector x is equal to the vector n dotted with the vector p. So n, that is 2, 3, and I take its dot product with x, y. That would then equal 2, 3, and that is dotted with the point, which here would be -1, 2, because p is the vector that points at the point -1, 2. And we know there's that nice correspondence between points in the plane and the vector. And that's it. That's the normal vector. That's the normal form of the line. It's not magical at all, and it's really not nice to write out. Now, just like vector form had an alternate form called parametric form, normal form has a way also, another way to represent it, getting rid of the vectors and focusing just on the components, which we call general equation of the line. This is the form that you learned way back in high school. So note the following. If you use these notations like we always have been doing, vector x is the vector components of x and y. That's the unknown point on that points to an unknown point on the line. You have the vector p, which points at the point x naught, y naught, which is a fixed point on the line. And then you have the normal vector, which is orthogonal to every vector that would lie on the line itself. The components for the normal vector we'll call a and b, just to be arbitrary. Now, if you just write out the normal form and just do the dot products, notice that the vector n dotted with the vector x is a times x plus b times y. And the dot product of n with p, those are all just numbers. They're just fixed numbers. So it's a sum of product of numbers. It's just a number. We'll just call it c. That's it. That's the general equation of the line, just like you learned way back when in high school. Let's just try one real quick. We just did this moments ago. I showed you that the normal form of this vector, one normal form of the line for this particular line, would then be 2, 3 dotted with x, y, and that would equal 2, 3 dotted with -1, 2. So if you just literally do the dot products, you then move on to general form. That'd be 2x plus 3y, and that would equal, that'd be -2 plus 6, and that is 4. So that's 2x plus 3y, that equals 4. And that's the equation of the line. That's just a general form of it, like you learned way back when in high school. You now know 4 different ways to represent a line. One would be the normal form and the general equation of the line. It's easy to go between those two. And the parametric form and the vector form of the line. Again, it's easy to go between those two. You need a way to sort of relate all 4. To do that, all you need is to know the connection between the normal vector and the direction vector. So let's go back and look at those again a little more closely. The direction vector, it just describes the relative change in x and y. M1 is the change of x. That's the first component of D. M2 is just a change in y, the corresponding change in y, and that's the second component of D. So because of that, the slope of the line must be M2, change in y, over M1, change in x. Also, you notice, though, that if you take any multiple of D, that ratio of first component divided into second component, that actually won't change. That means then any multiple of D could also be a direction vector. So there isn't such thing as the direction, really. It's more like a direction vector. Now for the normal vector, let's just say the normal vector is given by components A and B. It's supposed to be orthogonal to every vector that lies on the line. Well, but that means then that N and D are orthogonal to each other. So that means their dot product is 0. But it also means, since their dot product is 0, that any multiple of N, its dot product with D would also be 0 by the algebraic properties of the dot product. So therefore, any multiple, any non-zero multiple of the normal vector is also another normal vector of the line. So there's no such thing as the normal vector. You actually only have a normal vector. There's many of them. So remembering that the vector n and d are orthogonal, that means their dot product is 0. That means you get that equation. Whatever a, b, m1, and m2 are, they must satisfy that equation. That also means, by the way, that since the slope is m2 divided by m1, by just solving for m2 divided by m1 in that equation you have on the left, you get the slope is also negative a over b. So you have some quick, easy ways to hop between all the different notations. Let's now review the forms of the line. So, to start, we have a line. We have a fixed point P, x naught, y naught on the line. We have a moving around point, we don't know where it is, Q, which is given by x comma y. Those points naturally correspond to certain vectors that start at the origin and point at these points. We call them in standard position. They're going to be called vector x and vector p. We want to describe the overall change to go from our fixed point to this variable point. I want a relationship for how to describe vectorially x minus p. To do that, you need a normal vector, which is just a vector orthogonal to every single vector in the line, or you need a direction vector, which is actually a vector on the line itself. Notice that n and d, their dot product is 0. The slope is given by m2 divided by m1, and it's also equal to negative a over b. Okay. In R2 only, when you get to R3, these formulas don't work anymore. In R2 only, you can write down the normal form of the line. So once you have the normal form, it's obvious to go from that to the general equation. So anytime you see that equation in R2, you know you have a line. Again, anytime you see that equation, that general equation, in R2, you have a line. If it's in R3, it's actually not a line, it's something else. But more universal, something that can be used always in any dimension, you have vector form. This always works. It doesn't matter if the vectors have 2, 3, 4, 5, 10 components. The vector form of the line is always given by x equals the vector p plus some multiple of the vector d. And then from here, if you want, you can get parametric form. The number of entries in the parametric form just depends upon, well, the number of components that you have. So if you're talking about a line in 3 space, then you'd also have a z equals something. But the form is exactly the same. It'd be z equals z naught plus m3 times t. Okay, now that we have gone through that, let's go look through a couple easy examples. I want to know, what is the vector form of this line passing through these 2 points? It's really pretty easy. You just got to draw it. So here is going to be point P, and it will be 1, 2. Over here, let's say you have point Q, and that will be 4, 7. I want the equation of that line in vector form. To do so, all we need is a direction vector, some vector that lies on the line. Well, one such direction vector is pretty obvious. It's literally just the vector PQ. So that is, take the overall change in x and take the overall change in y. That will then give you the vector 3, 5. For our vector p, it just has to go and point at or correspond to a fixed point on the line. Any will work. So I will use 1, 2. From there, we get then the vector form of the line. The vector x, which is p plus t times d, Or if you want it a little bit more explicit, it'd be the vector xy is equal to the vector 1, 2 plus t times the direction vector, which is 3, 5. And that is one way to write it down. Notice there's many direction vectors. You could take any multiple of the vector d, and that would give you another direction vector. It would give you an entirely different vector form of the line. It would still be the same line, still represent the same line, but it would be a different form. If you want, you don't need to use the vector p to be 1, 2. We could use the vector 4, 7 and build up the vector form that way. That would just be a different representation of the same line. My advice to you, though, is that if you ever want to use multiple representations, for each representation, just call the parameter something else. So use s and t and m and n and o and p. Just use different variables. That way, the association between the parameter and the point is unique for each representation. For t, you get a point. For s, you get a point, and so on. Okay, now let's go do another one. Let's find the general form of this line. Now, this line is currently given to you in parametric form. There's lots of ways to go from parametric form to the others. I'll just give you two different ways to handle the same thing. One is more of a brute force method, which people tend to like, and the other is more higher level, thinking about the pieces that make the vector, to find those pieces, normal vector, direction vector, and so on, and use those to find the equation of the general equation. So one way to do that is this. I have the parametric form. Parametric form has a parameter, t, in it. Well, general form doesn't, so let's just get rid of it. I'm going to solve for t in both equations. So if you do so, you would get x minus 3 over 4, that's t, but also t because of the second equation. T is also, didn't mean to write that. Can I get rid of you? Yeah, I can. I also would have y minus 2 all over negative 3. Just ignore the t now and cross multiply. You have negative 3 times x minus 3 is equal to 4 times y minus 2. You then have negative 3x plus 9 is equal to 4y minus 8. So you could have negative 3x minus 4y would equal to negative 17. All I did was bring all the variables to one side and all the constants to the other. That is a general equation of the line. That's not the only one, though. General equation of the line is just a one. There's many of them. Take that equation and multiply it by any constant you like, any non-zero constant, and you'd get yet another general equation of that line. So if you multiply the whole thing by negative 1, you would get this equation. It is also a general equation of the line. All right, that's one way to go about doing it. Another way, though, is to think of it this way. See, that can be written in vector form by doing this. And that tells you right away that the direction vector of this line is actually 4, negative 3. That means then that I can find a normal vector for the same line very quickly. So the normal vector, a normal vector, is just some vector whose dot product with d would then be, well, 0. Well, one easy example is just 3, 4. The dot product of n and d would be 0. That would be a normal vector for this line. So then from here, I can then quickly go to the general form by looking at the normal form first. Normal form would then be n dotted with the vector x. That would then equal p, which here, that would then be 3, 2. And that would then be dotted with n also. So just doing the dot product, that's then 3x plus 4y, and that equals 3 times 3 plus 2 times 4, and that's the equation 3x plus 4y equals 17. See, you get the same thing in the end. You get the same thing in the end. You can use either one. Both of these techniques are useful, though, because the method on the left really depends upon the way we represent vectors. The one on the right doesn't. It depends upon it less. The method on the right will be more useful long term. Okay, there you go. So that's another easy example. Let's just try one more. Same kind of little tricks. I want you to find the vector form of a line that passing through the point 1, comma -1, but it's perpendicular to the line I just gave you. Now, the line I just gave you, x minus 5y equals 1, that's a general form of that line. So because of that, I know automatically a normal vector for that line. The normal vector, would then be the vector 1, -5. Because right here is A, and right here is B. And the normal vector is AB. So if I have a normal vector, I could find a direction vector very quickly of this line. So the direction vector of this line would then just be, one example would then be 5, 1. That's a vector whose dot product with n is 0. So I have those things. I'm going to draw what we have so far. So here is some weird line. That's the line x minus 5y equals 1. I have some point out here in space. That point is 1, comma -1. This is the line I don't care about. The line I want is this guy right here. Oh, drat, I missed the point. There you go, I fix it. We'll call that line L. I want the vector form of the line L. Well, just think about it. I need a vector that's on L, but L is orthogonal to the line I gave you. Well, the normal vector here of the original vector, that's the vector n. That vector is orthogonal to the original line, which means it's on L. If it's on L, the direction vector for the line perpendicular to it is actually the normal vector. So then for my line, for L, I'll use the vector that points at the point will be the vector 1, comma -1. And the direction vector of this line is actually the normal vector of the original line, which would then be the vector 1, -5. So the vector form of this new line, perpendicular to the one I gave you, and passing through the point 1, 1, would have vector form xy is equal to 1, -1 plus, I'll use s, times 1, -5. And that's it. That is one potential vector form of that line. An understanding of the 4 different ways to represent a line in R2, we can now talk about the different ways to represent a plane in R3. The equations are pretty much all the same. It's just that you have more variables. You have to be therefore careful when you look at a certain equation. Are we talking about something in R2 or R3? So let's suppose you have some kind of plane in R3. Let's pick a fixed point P, which will be x naught, y naught, z naught in the plane. And then you have some kind of other point, x comma y comma z, that kind of roams throughout the plane. From here, it's natural to go from the origin to these 2 points to get standard vectors x and p. And then you have the vector going from p to x, which was the vector x minus p. We want to find some way to represent x minus p. So to do that, we're going to use 2 vectors for a plane. We only use 1 vector for a line. We use 2 vectors in a plane to kind of define the overall plane. Now these 2 vectors, u and v, they just can't be parallel to each other. So they're not multiples of each other. They go in different directions. These 2 vectors, if they're both starting at the point P as their initial point, will define kind of like a coordinate system in that plane. So any linear combination of these 2 vectors, u and v, will give you essentially every vector that's in that plane. One of those vectors being x minus p. So there has to be some linear combination of u and v that equals x minus p. It's just I don't know the scalars. We'll call them s and t. Notice that's really the exact same thing as the equation of the line. It's just we don't have the extra addition of t times v. It was only a vector times some scalar, not a sum of products being scalars times vectors. Okay, so that's essentially vector form if you just solve for the vector x. The next one would then be normal form. So it's exactly the same as we did before. We just assume that we have a vector n that's normal to every vector in the plane. Then notice that if it's orthogonal to every vector in the plane, then it's orthogonal to the vector x minus p, so their dot product is 0. And when you take that dot product, then you get n dotted with x is equal to n dotted with p, and that's the normal form of the plane. From these, it's very easy to go to general form of the plane in R3 or the parametric form of the plane in R3. So let's kind of just review that all at once. So this is in general, the vector x goes from the origin to the unknown point that roams around the plane. The vector p is a vector that goes from the origin to a fixed point on that plane, x naught, y naught, z naught. We have that n is a normal vector to that plane, whatever that's going to be. We almost always use a, b, and c. U and v are vectors that just have components, u1, u2, u3. V is v1, v2, v3. And n, being normal to the plane, is orthogonal to u and v. So n dot product with u is 0, n's dot product with v is 0. So then we have the easiest ones is in R3 only. The normal form is n dotted with x, and that's equal to n dotted with p. It's just not really very useful. We almost always go directly from normal form and literally just do the dot products. So n dotted with x, that would then give you ax plus by plus cz. And n dotted with p, being vectors just of particular constants, it's a sum of product of constants. We just call that d. So ax plus by plus cz equals d. That's the equation of a plane in 3 space. Notice it's very like the equation, the general equation of a line in 2 space. It just has one extra thing, one extra term. Okay, well now vector form is the vector p plus the unknown scalar t times u plus the unknown scalar s times v. And if you just go and take the right side of that equation and just literally multiply it completely out and then compare components, you get parametric form. X equals x naught plus u1t plus v1s, and y equals y naught plus u2t plus v2s, and so on. That's it. It's really the exact same ideas for the equations of the line. It's just one more dimension. Let's go ahead and do a couple examples, this time with planes. I want to know what's the general form of a plane that passes through the point 1, 2, 3, and has a normal vector of 2, 1, 5. Well, just write down what you've been told. So one particular point, which is on this plane, can be represented by a vector 1, 2, 3. And the normal vector of the plane is the vector 2, 1, 5. The vector x goes from the origin to the point in the plane. That would then be x, y, z, the general point in the plane. And the normal form of the line says that n dotted with x is equal to n dotted with p. So just literally just do that dot product. So you have 2x plus 1y plus 5z. That's the dot product with n and x. That has to equal the dot product of n with p. That's 2 times 1 plus 1 times 2 plus 5 times 3. And that is 2 plus 2 is 4 plus 15, that's 19. So you get the equation 2x plus y plus 5z equals 19. That is one general equation of this plane. If you take that equation and multiply it by anything, divide by anything other than 0, of course, you'll just get another general equation of that plane. And that's it for that problem. It's not very difficult. For the next one, a little more interesting, I want to know the vector form of the plane that passes through these 3 points. Okay, well again, it's just a matter of kind of looking at the right way. So let's say, for example, that we're looking at the plane a certain way. So this point here is 1, 2, 3. We'll say this point here, Q, is 1, 0, 1. And then you have another point here, and that is the point 1, 1, 1. I want to know the equation of the plane in vector form. Well, the equation of the plane in vector form requires that we have two vectors, u and v, that are both lying in the plane. So notice that this vector here, which I'll call u, that vector u is just the vector pq, and you can find it by taking the change of x, 1 minus 1, take the overall change in y, 0 minus 2, take the overall change in z, 1 minus 3, that's the vector 0, negative 2, negative 2. That would be one vector in that plane. The vector v, let's say I'll use this one because I felt like it. I could also use the vector qr or rq. I'll call that vector v. That vector is the vector pr, and that is found by taking the difference in the x's, the difference in the y's, and then the difference in the z's. So that gives you the vector 0, negative 1, negative 2. So these could be the vectors that you use. But just like with the line, there's a number of direction vectors. There's an infinite number of vectors here you can use. You can use any multiple of u that you like. It would still work. You can use any multiple of v you like. It would still work. As long as u and v are just not parallel to each other. They're just not multiples. So I will not use the vector I just gave you. Instead, I'll use the vector u, which will be negative 1/2 of the vector 0, negative 2, negative 2. So the vector I'll use is 0, 1, 1. So the vector I'll use, I'll call it v again. Now, so it's not confusing, I'll call it vector A and vector B. Vector B will then be, well, I'll use negative 1 times vector v. So that's negative 1 times vector v. That'd be 0, 1, and 2. These are the vectors I'll use to form the vector form of the line of the plane. So the plane is given by x is equal to the vector which corresponds to the point. So I can use any of the points. I'll use the point q because I felt like it. And then I add an unknown multiple of the first vector, which I'll say is 0, 1, 1. And then an unknown multiple, different parameter, of the other vector in this plane, which is 0, 1, 2. And that's it. That is one vector form of the plane. Saying the is misleading. There really isn't one. There's an infinite number. Infinite number. So that's it. My advice is that if you ever want to represent a plane using vector form, just use different parameters. So if you use one representation and you use s and t, when you use another representation of that plane, don't go and use s and t again. Use something else like n and m, or use a and b, or c and d. Just use different scalars. And that's it. That's how that problem is done. All right, we now have enough tools and objects and concepts to go tackle some more interesting problems, one that are outside the normal formulas that I've given you so far. So let's try to find the distance between the line 2x plus 3y equals 5 and the point 1, 3. I'm going to draw kind of what it looks like so you have an idea. Here is the line. That will then be 2x plus 3y equals 5. And then over here somewhere, that would be the point P, which would be the point 1, 3. That point's pretty huge. So then I want to know the distance between the point P and the line. So obviously, whatever that closest point would be, it could be like somewhere around here. That point, which I'll call, I don't know, it doesn't really matter. I actually never find this guy. I'll call it point B. And it's an unknown point. I just wanted the distance between these two. Okay. So notice, though, that that means that this is at a right angle, right? Has to be at a right angle. Well, that means that the vector PB, that vector is actually a normal vector of this line. It's actually a normal vector. I just need to know which one. I need to know just which one. Okay, so right away, though, by looking at the equation of the line, I know one normal vector. One normal vector is the vector, it's just 2, 3. because right here is A and right here is B. So we know what the normal vector of the line is, or at least one of them. So it's good. So the distance then between these 2 points is just a multiple of that vector. I just don't know what it is yet. Still, though, that doesn't really help us out, though. I need something more. To do that, come over here, call this point Q, and notice that if I were to look at the point where x is 1, y is 1. So this point 1, 1 is also on this line. Look at the vector that goes from Q to P. So the vector from Q to P, I will call the vector U. That's the vector from Q to P. That is, find the overall change in x, P minus Q. Then find the overall change in y. Then you have P minus Q. And that's the vector 0, 2. All right, so we have that vector available to us. Also, though, I know that there's a normal vector, which I'll draw quickly here in a different color. That'll be in, I don't want that color. Let's pick light blue. There's a normal vector that starts at P. What I want you to do is take these two vectors I just drew and put them together. So you have the normal vector, that's this guy. Then you have the vector starting from the point B. You have the vector which is U, and right here is the point B, P. I want to know what is this distance. I want right here. I want that distance. Well, to find that distance, I just need to know what is this vector. Hopefully it seems obvious to you that since this has to be a right angle also, that all I need to do is find the projection. I need the projection of U upon this normal vector. That's going to be the vector PB. So writing that down so you can see it, the projection of the vector U upon the vector N, that is actually the vector PB. But we don't want that. We don't want the projection. What we want is the length. So we want the length of the vector PB. So that would therefore be the length of the projection of U upon N. Let's just figure out what that means. That's the same as saying take the length of, well, the projection of U upon V is this. It's U dotted with N all over N dotted with N times N. Cool. But that, and I'm going to run out of space, I'm going to continue over here. That then is equal to, I'd have the scalar U dotted with N all over N dotted with N. Well, but if you remember, N dotted with N is actually just the length of N squared. So you have the length of N squared, and you take that outside the length. When you do that, you put everything in absolute values. So I take the absolute value of the top and the bottom. I don't need the absolute value of the bottom because it's already positive. That's then multiplied to the length of N. But N is not the zero vector, so I can cancel part of this multiplication to get the absolute value of U dotted with N all over the length of N. And that's it. That's actually the formula. In fact, that's the general formula. If you wanted to find out then how to go about finding the distance between a point and a plane, you just need to know one of the point. You need 1 point on that line to find the vector U, which goes from the point on the line to the point off the line. So in this particular problem, that dot product, we have U dotted with N. So it's 0 times 2 plus, I then have 2 times 3, and that's all over the length of N, which is the square root of 2 squared plus 3 squared. So your answer then is 6 over the square root of 13, which of course you can rationalize. That's it. That's the distance between the point P and B. Nice, right? Okay, so now I've shown you that there are other obvious ways, to go and investigate these problems. There's relationships between lines. You could say, hey, when does this line intersect that plane? When do these two lines intersect? Do these two lines intersect? If these two lines intersect, they make what kind of angle? There's all kinds of problems that you can tackle now. It's just a matter of you putting together all the different facts I've given you. You're welcome to go try the homework now and to see how things go.